Hello, everybody. Welcome back to Intro to Physics. This is day 17, 18. I had the number in my head and then I lost track of it, but I think it's 18. So we have just a couple of days left to go through the rest of our energy unit, and then next week we'll be kind of wrapping things up with momentum and some additional topics, whatever we can squeeze in there. So today, without further ado, we're just going to pick up where we left off yesterday. So we were talking about gravitational potential energy yesterday. And we were just about to start talking about forces other than gravity. So that W sub other term. But do you guys have any questions from yesterday that we did not get a chance to answer? Going once, going twice.
Why do we use the same symbol for kinetic energy as Kelvin units?
There are only so many letters, but you're right. Capital K is also Kelvin, and kinetic energy. I'm trying to think if it's anything else too, but usually you'll see that we have the same letter as a variable and as a unit, like capital W for work and for watts. Capital G, for example, for universal gravitational constant, and Gauss as the unit. And that's just because there are only so many letters that we can have. So once we exhaust our alphabet and the Greek alphabet, we kind of have to start repeating things. Okay. Well, let's go ahead and keep going then. So when we have forces other than gravity that are doing work on the system, like I said, that's that W other term in our equation. So now we have this total work done on the system as being the work done by gravity and the work done by other forces. And that equals the change in the kinetic energy. So revisiting this work energy theorem, because this really is fundamental to this whole chapter. So that means our conservation of energy equation changes a little bit now. So yesterday we were ignoring this W other term and we just had initial energy. So K1, kinetic energy 1, plus gravitational potential energy 1 equals K2 plus UG2. But now we have this additional factor to consider of this other force. Which often is air resistance or friction, but it could be something else as well. So this means that the work done by all of the forces other than gravitational forces is equal to the change in the total mechanical energy of the system. Right, so this initial mechanical energy, remember total mechanical energy was K plus U. So initial mechanical energy plus that work done by other forces equals the final kinetic energy. I'm sorry, the final mechanical energy. So if this other work is positive, that means the energy is going to increase, or we have energy kind of added into our system. And so our final amount of energy is greater than our initial amount of energy. And then vice versa, when that other work is negative, the energy is going to decrease. But keep in mind, we're still not destroying energy or creating energy. It's just kind of transferring in from something else or transferring out to something else. Right. So when we're dealing with friction, for example, friction doesn't destroy energy, but it does turn it into heat, which kind of removes it from our usable system. Okay. And then if no other forces than the body's weight are doing work, then that other force or that other work that we're considering is zero. So our total energy is constant and we're dealing with straight up conservation of energy, which is what we like. So I'm going to revisit this problem solving strategy. It's the same one that we had talked about way in like week 1, the IC strategy. But it's been a while since we went through what that means. So let's just kind of apply that problem solving strategy to energy. So first we want to identify. So that's not just identifying what quantities and variables were given in the problem, but also identifying what method works the best to solve these problems in general. So some of the problems that we had done yesterday, those example problems, we could have solved with energy, which I did because that was the topic of the day, but we could have also solved them using Newton's laws or projectile motion or momentum. There are lots of different strategies that you can use to solve some of these problems. So you want to identify, based on what we're given, which strategy, which method works the best. So when we're dealing with energy, energy is usually the best approach when we're using forces that are not constant, or if we're talking about motion along a curved path as opposed to in a straight line. However, if the problem involves the passing of time, then energy is not usually the best method to use because we don't have equations of energy with time in them, except
You
that
have to use the kinetic equations for that.
you could. That would be one method that you could do. Absolutely. Newton's laws also does have time kind of hidden in them, right? Because they have acceleration, which is how the speed changes over time. So that might be a roundabout way to do that. But yes, if it involves time, probably projectile motion is a better strategy than energy, or at least a more direct strategy. After we identify the variables, what we're looking for, what our method is going to be, then we can set up the problem. So not to sound like a broken record here, but it is always best to draw a picture of your scenario, right? So we want to decide what those initial and final states of the system are. And so you can either use the subscripts 1 and 2 if you like that, or you can use I and F for initial and final, whatever helps you stay organized in your brain. We want to define our coordinate system and figure out where our 0 height or our reference height is. And you can choose that to be wherever is most convenient. But for the sake of convention, it's best to always assume that positive y is up and negative y is down, because that's sort of built into our equations. Now, you don't have to do it that way by any means, as long as you keep it consistent throughout the whole problem. But it might be a little bit easier to make mistakes if you change that convention. So the way that I will always do it is with positive y being up and negative y being down. We want to figure out all of the forces that are acting on our object or on our system, and all of the ones that are doing work that is not described by gravitational potential energy, right? Because that'll be our W other term if that applies. So here's where a free body diagram could be very helpful. And then we want to list what we know, what we don't know, and figure out what it is that we are looking for. Once we have all of that set up, now we can execute the problem. So finding our equations that we're going to use, start plugging in our numbers. In terms of energy, we're going to write expressions for initial and final kinetic and potential energy. So initial total mechanical energy and final total mechanical energy. And then using that work energy theorem, we can relate those two together. And if there's work other, then we can take that into account as well. Now, yesterday I had shown you just a quick example of one of these bar graphs that's referred to in that second bullet there. So a bar graph that shows the initial and final values of kinetic energy, gravitational potential energy, and total mechanical energy. So you can see how that energy kind of changes from one form to another throughout the course of the problem. And then we'll solve those those equations to figure out whatever it is that we need to find. Now, this last step is the one that is most often skipped by students, but you should make a habit to not skip this, and that's the evaluate stage. So we want to see whether or not our answer even makes sense. So check the units, make sure that they are consistent in your equation, make sure that you remember to convert your units if that was something that you needed to do, and then figure out if your like positive and negative sign makes sense. So the work that's done by each force must be represented somewhere in the problem. Either it'll be gravitational potential energy, or it'll be included as other work, but we don't want to include it in both places, just in one of those places. Right, so our gravitational work is included in gravitational potential energy. So we will not include it again as work done by something else. So just keep those things in mind. Okay, so here is an example for you guys. I fire a cannon from the top of my 18.5 meter castle. I have a castle, how cool is that, right? The cannonball is shot at 130 meters per second. How fast is it going when it hits the water below? So your first instinct, or at least my first instinct when I look at this is, oh, we're firing something out of a cannon. Obviously, this is projectile motion. And that's true, right? You could use projectile motion here, but you don't have to. We could use energy. And if the energy equations make more sense to you, then you're welcome to use that method. Of course, if projectile motion makes more sense to you, you can do that as well. You can do both and check your answer. Good strategy there too. But since we're in the energy unit, we're going to focus on the energy method. So here's our picture, right? My block-like castle. And here's our cannonball. It's being shot out and it is going to hit the water below. So we know it's being shot at 130 meters per second. We don't know what angle it's being shot at. So that's kind of tricky. Victor, I saw you raise your hand.
I was going to ask just now if do we assume that the angle is parallel to the ground, or should we expect them to give you the angle?
Yeah, and that's a great question. That would be one if you're like working on this as a homework problem or a test problem, you'd want to clarify that with your professor, because we don't want to just assume that it's horizontal since it doesn't state it. But since it doesn't state the angle, we don't know what the angle is. So that's where this kind of becomes a little bit tricky. And that's why I think energy is a better method here, because we don't need to know the angle for energy. We know that it is a height of 18.5 meters. And so just for the sake of convenience, I'm going to have the water level be my reference height of 0. Okay, so using this energy method now, the change in the energy is going to be equal to any of those outside forces, the external forces that we're not considering. Now, I didn't give you any way to calculate friction or air resistance or other forces. So for the sake of this example, we're just going to ignore them and assume that they're negligible since we weren't given any information about them. So that means that the change in the energy, so our final energy minus the initial energy, is 0. Right? There's no outside forces that we're considering. So our final energy is kinetic energy plus potential energy. Our initial energy is kinetic initial minus potential initial. And so that equals 0. Since the cannonball is ending up in the water at our height of 0, we don't have a final gravitational potential energy, right? Because that takes into account the height of the object. And if the height is at the reference point, then the height is 0. So that term is going to disappear. But we're left with these other terms. We know that there is going to be some final kinetic energy because it will be moving as it goes into the water. There is an initial kinetic energy because it's being fired into the air as opposed to being dropped. And there is an initial potential energy because it is a height above that water level initially. So plugging in our equations for those things, kinetic energy is 1/2 mv squared. And potential energy is mgy or mgh, if that's what you're more familiar with. Now you'll notice that in each of those terms, there is a mass, so you can cancel out those masses, which is great because you weren't given any information about the mass of the cannonball. That's because it's not actually important.
I have a question.
Sure.
What does he mean by the cannonball being parallel?
If
the ground.
we launched this cannonball horizontally, then our angle would be 0 and it would just kind of travel sideways and then into the water.
So if we launch it straight out?
Yes, if you launched it straight out, it would be parallel to our water level.
Okay.
Okay, so I took that equation, and remember the variable that we're looking for here is how fast it's going when it hits the water below. So that's this VF, the final velocity. So I did some algebra, multiplied both sides of the equation by 2 to get rid of it on this left side. And so then I plugged in my numbers there. Okay, so when we go through the math, we should get a final velocity of 131.4 meters per second. Now, does this answer make sense? Well, if we look at how fast it's going initially, right, 130 meters per second, by the time it reaches the water surface, it probably is moving a little bit faster. So that velocity of 131.4 meters per second makes sense, right? Some of that potential energy, or all of that potential energy that it had at the beginning, has turned into kinetic energy by the time it reaches the bottom. So it would make sense that our velocity is a little bit faster if our kinetic energy has been increased. Yes, Victor.
With this information at hand, could you possibly use this to back calculate what the initial launch angle was?
Yes, you could then like reverse your way through the problem and find other information if you needed to. So you'll also find, and that's a good point too, I'm glad you're bringing that up. You might find that you use multiple methods throughout the course of your problem. So like if this is part A of a homework problem, for example, and part B asked you how long it took to reach the water, then we might start part A with this energy method and then do part B using projectile motion. So yeah, just look at what you're given, figure out how you can get to what you want based on what you have. Okay, so here's another example for you guys, and I want you to think through this on your own before we talk about the answer together. So we toss a pencil to the ceiling. The pencil hits at 3.1 meters per second. The ceiling is 2.5 meters above the floor, but I throw it from 0.9 meters above the floor, right? So I'm sitting up or standing up and I throw this pencil up. If the floor is my reference point of 0, then my hand is not at the floor when I throw it. Okay, it's at a height of 0.9 meters above the floor. So try to think through these questions. What is the change in height of the pencil? What is the initial velocity of the pencil? And should the mass of the pencil change how fast you have to throw it? So think through those real quick. I'll give you maybe 30 seconds and then we'll come back and talk through those answers together. All right, so let's think through some of these answers together. So first of all, how fast did I throw it? That's an important question to figure out. So here we are. Here's the room. And I'm throwing the pencil up to the ceiling. It hits at 3.1 meters per second, but I don't know how fast I threw it. What I do know is that the height of the ceiling is 2.5 meters above the floor. and the height of my arm is 0.9 meters above the floor. So in this case, we can't just say that kinetic energy equals potential energy. We need to first ask ourselves if there are any other outside forces that might be influencing this system. But once again, since I didn't give any information about friction or air resistance, we're going to assume that those are negligible. And so our work done by other forces or outside forces is 0. Okay, so that means that the change in our kinetic energy plus the change in our potential energy is 0. Energy is conserved. Right, so our change in kinetic energy plus our change in potential energy is 0. Okay, so plugging in those equations for kinetic energy and for potential energy, again, we'll notice that there's a mass in each of those terms, so we can cancel that out. Okay, so here are the things we know. We know the final velocity is 3.1 meters per second. We know the final height is 2.5 meters above the ground, and we know the initial height is 0.9 meters above the ground. Okay, so once we plug in those things, just for the sake of space, I didn't plug them in on this slide, but once we plug in our variables and go through that math, we should get an initial velocity of 6.4 meters per second. So let's think, does that make sense? Well, we know from projectile motion that when an object travels up into the air, if the only force acting on it is gravity, then that object is in free fall, right? And so as we let go of it, the object is going to be slowing down as it reaches its peak, and then it would speed up as it falls back down. Okay, so we
I have
know
a
we're
question.
going to need to start with a faster speed than it will have at its peak if that object is going to be slowing down as it rises and speeding up as it falls back down. So the fact that this velocity is bigger than our final velocity should be reassuring.
I have a question.
Yes.
How come you can't let it be like kinetic energy is equal to gravitational potential energy?
That is not a safe assumption to use in every scenario. So we don't want to just go into energy problems with the assumption that those two things are equal to each other, because they may not be. We have to ask ourselves if there are outside forces that would be removing energy from the system that we also need to consider, like friction, for example. Right, so we don't want to just jump into this immediately saying that they're equal to each other. We have to go through that step right here of asking, are there other forces that are at play here that might change that? Once we establish that there weren't, that's when we could say the change in kinetic energy was equal to the change in the potential energy.
We're just saying that there's no other forces for the sake of the question, right?
I'm sorry, can you say that again?
We're saying that there's no other forces for the sake of the question, like
Yes.
air resistance doesn't exist, all that.
Right. Yeah,
Okay.
there's no normal force once it leaves our hand. There's no air resistance. There's no friction. There's, yeah, none of those other applied forces that we talked about. It's a pretty straightforward problem. Okay.
Oh, I have one more question.
Sure.
How can we make it the equation equal to 0?
Because since there's no external forces that we're considering, that means energy is conserved. So the initial kinetic energy, the initial total mechanical energy that we're starting with equals the final total energy, right? And so if the initial energy equals the final energy, then we can move the final energy over to the left side of the equation as well, and it will equal 0. Victor, I see you raise your hand.
Just double checking for G, we're setting value equal to negative 9.8, correct?
Yes, G is 9.8.
Is it negative?
I don't think I made that assumption in the math.
Do
But
we
you're
have to?
welcome to, depending on how you establish your coordinate system.
Got it. Thank you.
Okay,
Uh,
let's take a look. Oh, yep. Is there another question?
yeah. I'm still having trouble like trying to like visualize how come it's equal to 0.
Okay. I do not have paper on me to write it out for you. But I'll try to use my mouse and we'll see if that works. Okay, so is it this line right here that you're asking about?
Yes.
Yes, okay. So remember this E right here is the total mechanical energy. So that's kinetic plus potential, right? And this is the change in the total kinetic energy. I'm sorry, the total mechanical energy. So if there's no outside forces that are acting on the system, no outside work, then energy is conserved and the initial amount of energy equals the final amount of energy. So the change in the energy is 0, right? The change
Yeah.
in total energy is 0. So going down to the next line then, if this energy considers the kinetic energy plus the potential energy, then delta E is delta kinetic energy, the change in kinetic energy, plus the change in the potential energy. And if delta E equals 0, then this sum equals 0. So right here, I'm just writing out the definition of change in total energy. And so this line is basically just telling us energy is conserved throughout the course of this problem. The total
So
amount at the beginning equals the total amount at the end.
so if I put back what we got for velocity, it will equal 0 on the other side.
I'm sorry, can you say that again?
If I put back what we got for velocity, it will equal 0 for the other side.
Yeah, so if you plug this into our equation, and plugged in all of those other numbers, it should give you 0.
I'm ooh. I guess it's just like I'm just really confused because it's like having to put other things too, like the friction too. And like
So we're not
this,
considering friction yet.
I understand, but like have like it's also like the very top one that's I feel like that's confusing me the most, I guess. I don't
This very top one or this
Mm.
very top one?
the one where your cursor is right there.
W other?
Mhm.
Okay.
Yeah.
Yeah, so that's just saying in this problem, we are not considering friction. Basically, that's what that is telling us. So the outside forces, anything that's not gravity, we're ignoring. It's equal to 0. Right? So we are only considering the work done by gravity and not the work done by anything else. I don't know if
I
that helps you at all,
Mhm.
but maybe seeing some more examples will help you.
Okay.
Okay. So I'll go through some more examples, and if you still have questions about it at the end, feel free to ask me. But yeah, let's go through some more examples, and I think seeing the patterns in the thinking and the logic will kind of help figure things out. Fingers crossed. Okay, so here's another example for skateboarding. A skateboarder coasts at 8 meters per second on flat ground, then encounters a long ramp. How high does she get on that ramp if she just coasts? Okay, so just coasting means she's not like actively pushing.
She's not accelerating.
She is not applying a force. we don't want to say that she's not accelerating, because if, like, imagine riding a skateboard, or if you've never ridden a skateboard, like imagine riding a bicycle up a hill or something, right? You know that if you go up a ramp, if you're not pedaling or if you're not actively pushing that skateboard, you're going to slow down, right? And that slowing down is still an acceleration. So I don't want to say she's not accelerating, but I am going to say she's not applying a force. Okay, so she's going on flat ground, and then goes up a ramp, and she's going to slow down as she goes up that ramp. Okay, so we want to know how high she gets on that ramp if she's just coasting and not actively pushing or actively applying a force. Okay, so once again, we're going to start with this question, I guess. Is there outside forces acting on this object? And if there are, then the change in the energy is going to be equal to that outside work. Okay, so in this case, we're going to make an assumption that friction does not exist, which is a terrible assumption to make. But for the sake of argument, we're going to say friction does not exist. She's just going up a frictionless ramp, a very, very slippery ramp. Okay. So that means that our change in energy is 0. Because again, I did not specifically tell you, please consider friction in your example. So usually, if they don't explicitly say, consider friction, then that is permission to ignore friction in physics 1. Okay, so if this is true, then if our assumption is true that there is no friction, then there's no outside force acting on it. That means that our initial energy equals our final energy. And so we would have conservation of energy. There's a question in the chat. Is it safe to say that slowing down is negative acceleration? Yeah, that's usually how I define it. Okay. So our initial total energy is our initial kinetic energy plus our initial gravitational potential energy. And likewise, our final energy is our final kinetic energy plus our final gravitational potential energy. So if we look at the scenario, we'll see that initially the skateboarder is on the level ground. And I'm going to just establish that to be my reference height. So the ground is my reference height, which means that before she goes up this ramp, being on that ground, on that reference height, means she has a potential energy of 0. And if we're interested in how high she gets on that ramp, if you think about it, right, the highest that you're going to get is right before you start rolling back down. So right at that moment that she's at the highest point on the ramp, her velocity is going to be instantaneously 0, right? So she's going from up and about to start going back down. In order to do that, she has to stop momentarily before she starts rolling back down. So that means our final kinetic energy up here somewhere on the ramp is equal to 0, because that speed momentarily is equal to 0. Okay, so this is a skill that's very helpful to learn, just by looking at the situation, trying to figure out which types of energy are present at which locations. Okay, so really, we're only dealing with an initial kinetic energy because she's moving along that level ground, and a final gravitational potential energy because as she's up the ramp, that means she's above the level ground. So she has that potential to fall. Okay, so that means 1/2 mv squared equals mgy. So once again, we see that there's a mass in both of those terms. We can cancel it out. And we're looking for the height, that YF. final height. So we'd have 1/2 times that initial speed squared. Initial speed is 8 meters per second squared. And then we divide that by g to get our final height of 3.27 meters above the ground. What questions do we have about this example?
I'm still a little bit lost to like how to figure out if it's gonna be equal to each other or just equal to 0.
Like this step right here?
Mm-hmm.
These statements are equivalent to each other, right? If the change in energy, the final minus the initial energy, is 0, that means the energy is conserved. So we can just take this initial energy and add it to both sides of the equation, just algebra manipulation. So we can take this initial energy, move it over to the other side, and we'd have final energy equals initial energy. So that tells us that energy is conserved throughout the problem, and it will just change from kinetic to potential back to kinetic, but we're not losing any of that energy to things like heat or sound or friction, those types of things.
I have a
So
question.
yes,
Are we canceling out the initial potential energy and the final kinetic energy just because like the statements are the same? So if you cancel one out on both sides, they're still going to be the same. Or it's like simplifying it.
we are simplifying it. That's not the reason why we're canceling them out, though. The reason we're canceling them out is based on how I've established my coordinate system. So I've established my reference level to be here at ground level.
So there's no potential energy
Right, which
initially.
without that potential energy. Yes. And so then when the skateboarder is all the way up as high as she's going to go on that ramp, she's momentarily stopped before
So that's
she's.
0 kinetic energy.
Yes,
Okay, I see. Thank you.
you're welcome. Okay.
I'm really confused between these two slides.
This one and example 4.
Mm-hmm.
Okay. For the sake of time, we will come back to them at the end after I stop the recording, if that's okay with you.
Yeah.
Okay, cool. Don't let me forget. Remind me.
Okay.
Okay. Okay, here's another example. And this time we are going to consider friction. Okay, friction will be doing work. So I shove a box across a mostly smooth floor at 2 meters per second, let it go, and wait for it to slow down and stop. The coefficient of kinetic friction is 0.15. Okay, so right there in the problem statement, it should be fairly obvious to us that yes, we do need to consider friction because it's explicitly telling us about the coefficient of kinetic friction. So that's a big clue right there that yes, friction is applicable here. We can't just ignore it. So are there any external or other forces acting on this box after I let it go? And will that provide work on the system? Yes. And yes, right? Yes, there is an external force that we have to consider now, and that is friction, because friction is going to keep working on this box even after my hands are off of it. It's friction that's going to make it slow down and stop because this box is moving along just a flat floor and it's still slowing down. Okay, so that's friction that's taking energy out of the system. Now the question, will that provide work on the system? Yes, that friction force is acting on the object as it's covering a displacement. So that means that it is doing work. Okay, if you remember from, is that Monday when we had those examples with the sled and that sort of thing, when we were figuring out if friction does work? Yes, it does. Okay, and work is force times displacement times the angle between the two of them. We'll get into that in just a minute. Okay, so some other questions to consider before we just dive into calculating this problem. We want to know if that work done by friction is going to be positive or negative. So is it adding energy into the system or is it taking energy out of the system? Is there any change in gravitational potential energy that we're dealing with here? And is there any change in kinetic energy that we're dealing with here? Okay, so these questions should be fairly simple to answer just by reading through the problem statement. Is this work going to be positive or negative? Negative. The friction is slowing down the box. So it's taking energy away from the box, and that is a negative work. Is there any change in gravitational potential energy to deal with? No, because this floor is flat, and so it's not changing height at all. So there's no change in gravitational potential energy. Is there a change in kinetic energy? Yes, because the speed of the box is changing. Okay, so now that we know those things, setting up the problem should be a little bit simpler. So here's our box and our floor. Initially, it's moving with a speed of 2 meters per second. That coefficient of friction, which has that symbol
Mu.
mu, yeah, mu, is 0.15. We want to know how far it coasts before it stops. That if we set that floor to be our reference level of y = 0, then that I think is most convenient for this scenario. So now we're going to ask that question to ourselves again, just like we did in the other examples. Is that change in energy equal to outside work? Is there outside work acting on this system other than just gravity? Right? And the answer to this question in this case is yes, absolutely. And that is friction. Okay. So now the change in our energy is not equal to 0 because there's work done by friction. Now that change in our energy is equal to the work of friction, which is force of friction times the displacement times the cosine of the angle between the force and the displacement. Okay, so for this question, there's no gravitational potential energy because the surface, the floor, is where I established my 0 point. That means the gravitational potential energy is 0 at each point of its motion. So we can completely ignore it from this problem. So we're only considering now the kinetic energy, which is present because it's moving, and that work done by friction. Now, the way that we calculate friction, we learned last week in Newton's laws, is mu, that coefficient of friction, times the normal force. And then we just move those other terms down, the d cosine theta. Okay. The final kinetic energy is 0 because it slows down and stops. So once it stopped, it's no longer moving. The speed is 0, so the kinetic energy is 0. Okay. The angle between the friction and the direction of motion, remember, friction opposes motion. So that means they're at an angle of 180 degrees from each other. And so the cosine of 180 degrees is -1. So that's where this negative sign comes in this equation, right? So the cosine of 180 degrees is -1. Okay, so now we have negative kinetic energy from here equals negative coefficient of friction times normal force times the displacement. Okay, so we know that kinetic energy is 1/2 mv squared. Mu we were given in the problem. The normal force, since this box is sitting on a level ground and the box is not being like dragged through the ground and it's not being lifted into the air by anything else, that means the normal force is equal to the force of gravity in this case, which is mass times g. And then we have that displacement again. Now, since we had a negative sign on both sides of the equation, I canceled those out and removed them in this line. Okay, so you'll see that there's a mass on both sides of the equation, just like there have been previously. So we can cancel that out. And we're looking, in this case, for the distance that it traveled, or the displacement. So to find that, we have the 1/2 v squared. So here's the 1/2 v squared. And then we divide both sides by mu and g. So divide by mu and g. Okay, our initial speed is 2 meters per second. We need to square that. Divided by 2, divided by that coefficient of friction, divided by 9.8 meters per second squared. That gives us a displacement of 1.36 meters. Okay, any questions about this example? Victor?
Does knowing what equation to apply in the given question come with experience?
Yes, absolutely. The more you practice this, the more you'll see the patterns and the more you'll know which equations to apply, which is why I do example problems with you guys and why I post practice problems on Canvas for you guys to try. It really does come with practice. Yes, Ayana.
So when we start the actual physics course in like college or high school, will we be given like a sheet with all the equations, or will we have to like compile it as we learn?
Most often you will have to compile it yourself. There may be some cases where the professor will give you an equation sheet. However, from my experience, the equation sheets that you make yourself are much more helpful than the ones that the professors give you.
Yeah.
So most of the time they'll tell you to create your own equation sheet, and that way they'll know that you put in the effort to study, right? A lot of the time they'll require it to be in your own handwriting as well. But then that does also enable them to be more lenient with partial credit, because they know that you've put in the effort to create your own equation sheet.
Okay, thank you.
But I don't think I've ever been in a physics class that did not allow an equation sheet of some sort. I've been in math classes that did not allow equation sheets or calculators, but not a physics class at FIT. Okay. Cool. So here is, I believe, our last example that we'll have time for today, but this is a complicated example. This one is advanced. This is like your test problem, final exam type problem. Okay. There's a lot going on in this one. So here we go. Example 7, Atwood machine. A box of gravel with a mass of 130 kilograms slides on a rough surface. Okay, right there, that's a clue. Friction is involved. If we have a rough surface, that means there's friction. Okay, and we can tell that from the picture there too. The coefficient of friction is given to you. Anyway, it slides on a rough surface being pulled by a bucket of concrete with a mass of 65 kilograms. Sorry, the G is missing there. It should be kilograms. Find the speed of the box of gravel after it has moved 2 meters. The system starts at rest. Okay, so in Physics 1, since I've been a GSA or a teaching assistant for Physics 1 lab, I can tell you that we do have Atwood machine experiments that you do in Physics 1 lab. So this is a type of problem that you will see again for sure. Okay. So since there's a lot going on in this problem, I'm going to color code my terms in the equations. So if you are colorblind, I'm terribly sorry if this makes it confusing for you. That was not my intention. But anything that pertains to the box of gravel is going to be in orange font, and anything that pertains to the concrete bucket is going to be in red font. Okay, so at rest, remember that's a key phrase to pull out from the problem statement. At rest means that initial velocity is 0. So what does that tell us about the initial kinetic energy? it's also zero, right? If there's no speed initially, then that initial kinetic energy is zero. Okay. Another key thing to know is that these two objects are connected to each other with a string or a rope. And that rope, we're going to assume, does not stretch, right? It's not a spring, it's not a slinky or a bungee cord or anything. It's just a normal rope. So that means that if this box is traveling 2 meters, the concrete bucket is also going to be traveling 2 meters, in this case downward, right? But this string is not going to stretch. That also means that these two objects are going to be moving at the same speed as each other the whole time. Otherwise, like if they weren't, then this string would stretch or it would compress, which is not the case.
I think I remember the equation for the Atwood machine.
Oh,
For
good. Yeah,
this
you've
one.
seen it before. That's great.
Can I tell it?
Is it pertaining to energy or forces?
It's pertaining to how we're gonna solve this problem.
Sure, if you want to give it a try.
Okay. So if I remember correctly, it's like mass 1 plus mass 2, and then those two are in parentheses times velocity initial equals mass 1 and mass 1 velocity final plus mass 2 velocity final of mass 2, which is the base, which if I remember correctly, that's like the base form of the equation for Atwood machines.
Yeah, so that's the equation that you will see in your physics 1 lab class. If I followed it correctly in my head, if I visualized it right. That is an equation for Atwood's machines, absolutely. And I'm glad that you have experience with these because you'll get more experience with these in the future. Okay, so let's write it out then, so we can all see it together. Okay, we have to consider both objects this time because now there's not just one object in the system, there's 2 objects. So we have to look at both of them together. Okay, so again, we're going to start with this kind of question. It doesn't have a question mark, but it's still a question. The change in energy, is there a change in energy due to some external force? And yes, there is a change in energy due to friction, right? We saw that with the rough surface. We see that in the picture with this coefficient of friction. We do have friction that we're considering as our other work. And this time our change in energy of the total system is now the change in energy of our first object plus the change in energy of our second object, right? Our system involves 2 objects now. So we have 2 terms for that. Okay, so we can break that down even farther, just like we did in the previous examples. The total change in energy for the first object, the gravel box, is the change in kinetic energy plus the change in gravitational potential energy. And similarly, with our second object, that concrete bucket, the change in its energy is the change in kinetic energy plus the change in potential energy. Right, so I'm using this subscript 1 as object 1, the box, and the subscript 2 as object 2, this concrete bucket. Okay, so we know that this gravel box is going to be moving across the surface of the table the whole time. And so that's where I'm going to establish my reference point to be, just to be able to simplify something in this equation, because otherwise it gets to be quite a lot to look at. So if this table level is my reference height of 0, that means this gravel box, as it slides along the table, is not changing its gravitational potential energy at all. So we can immediately cancel out this term. Right, the gravitational potential energy does not change because this gravel box's height is not changing. Now that's not true for the concrete bucket. The concrete bucket will go down as this gravel box slides. So we have to leave this term in there. We can't cancel that potential energy out. But we do know that if this gravel box is moving 2 meters, then that concrete bucket is going to be falling 2 meters. And if the height of this table is my reference height of 0, then we know that this concrete bucket is going to be moving through a negative distance of 2 meters. So it will fall down 2 meters. Okay, that's going to be our change in y that we use for this term here. So since we're dealing with the change in energy in each of these terms, that means we're dealing with final minus initial. And final minus initial kinetic energy for the bucket, and final minus initial potential energy for the bucket. Okay, but we do know that this system is starting from rest. So that means, like I said before, the initial kinetic energy of both of those objects is 0, which is awesome, right? So we can get rid of those two terms. And we're going to assume too that this concrete bucket, if we like shifted our system a little bit, so this box is slid back over and the bucket has been raised up to the initial points. If that concrete bucket is falling from table level, then its initial gravitational potential energy is 0. Right, so we can cancel out those two kinetic energies because the system starts at rest. We can cancel out that initial potential energy because it's starting from a height at 0 from which it will fall down, but it's starting from a height of 0. Okay, so now our equation has been simplified quite a bit from those that choice of our coordinate system. All right, so kinetic energy, 1/2 mv squared for our first object. Kinetic energy for the second object, the bucket, 1/2 mv squared. And potential energy final for that bucket, mgy. Remember the subscript 2 means that second object to the bucket. Subscript 1 means the first object, which is the box. Subscript F means the final. So final kinetic energy, final kinetic energy, final potential energy. Okay, in this case, we cannot cancel out the masses like we did in the previous examples because we're not talking about the same object in each of these terms, right? In this first term, we have the gravel box. This second and third terms are talking about the concrete bucket, and they don't have the same mass as each other. So we cannot cancel out that variable this time. So we're going to remember that since these two objects are connected to each other with a string that is not stretching or compressing, they are moving at the same speed, which means the final velocity of the first object, the box, equals the final velocity of the second object, that concrete bucket. So we can just call that final velocity. It's the same for both objects. The work done by friction, which we saw in the previous example, is mu, the coefficient, times the normal force, right? Mu n is how we calculate the force of friction, times the displacement, times the angle between the force and the displacement, which is 180 degrees. Okay, so plugging in some things that we know the mass of the first object, the box, is 130 kilograms. The mass of the second object, the bucket, is 65 kilograms. We know G is 9.8. We know the bucket is falling down a height of 2 meters. The coefficient of friction is given to us as 0.4. The normal force is referring to the box, right? It's the box that is sliding and experiences the friction. We don't have friction from the bucket because we're not dealing with air resistance here. We're just dealing with the friction of sliding, that kinetic friction. So that's why we're only considering these orange terms pertaining to the box in the calculation of the work done by friction. So the normal force, since this box is sitting on the table, not being pulled into the table or raised into the air at all, is equal to the mass times G. Okay, so 0.4 is our coefficient of friction. The mass, 130 times G, 9.8. It's going a displacement of 2 meters to the right, so that's positive 2 meters. but friction is acting opposite the displacement. So that's that cosine of 180, which gives us -1. So even with all of these numbers, you see there's really only one variable that we're trying to find here, and that's the final velocity, that final speed. It does appear in both of these terms, so you'll have to be careful with your algebra and the way that you type these numbers into your calculator. But you should end up with a final velocity of 1.62 meters per second. Right, and that pertains to both objects. Both of those objects are going to be moving with a velocity of 1.62 meters per second after this has slid 2 meters. So I recommend that you take some time. I know we're 5 minutes past 4:30 right now, but once I post this on Canvas, I recommend that you take some time, work through this math on your own if you haven't been following along with the calculator, and just make sure that you know how to do this type of algebra simplification for yourself. So this is by far the most complicated example that we've done so far. Do you guys have questions about this one? There were a lot of assumptions that we made to get to this point.
Me and you are still going to talk about the what I was getting confused at the beginning.
Yes, we can. But any questions about this example 7?
Oh, I'm good.
Okay, cool. Anybody else? Going once, going twice? Okay. So we will pick up here tomorrow with some kind of conceptual questions for you to think through, and then we'll talk through them together. But I hope you guys have a great rest of your day, and I will see you all tomorrow. Bye.
Have a great day,
Very
Miss.
much.